Hello, welcome to my presentation. My name is Narottam. The title of my presentation is Half-Wave Dipole Antenna. First of all, I'm explaining the learning outcomes. After successful completion of this module, you will be able to understand the basics of half-wave dipole antenna and its applications, able to analyze the performance of half-wave dipole antenna by calculating its characteristics or parameters, and able to design and construct simple half-wave dipole antenna for communication systems. And this is the outline of my presentation. Then I'm coming to the point, antenna. We need antenna every day we are using. So what is antenna? That is the question, because antenna is the device that can receive signal and transmit signal. So far, the region of transition between guided and free space propagation, concentrating incoming wave into a sensor for the receiving case, and launches waves from guiding structure into a space or ear for transmitting case, often part of signal transmitting system over long distance. So far, it is not limited to electromagnetic waves, example, acoustic waves also. So far, the introduction, antenna is an electrical conductor or systems of conductor. Here, the transmission, that is, radiates electromagnetic energy into the space, and reception collects electromagnetic energy from space. It is a two-way communication system. Same antenna can be used as transmission and reception. Transmitting antenna and receiving antenna. This is transmitting via the channel. Then I'm coming different types of antenna. So in antenna, so isotropic antenna as idealized, it radiates power equally in all directions. And then dipole antenna has half-wave dipole antenna, a Hertz-type antenna, as well as quarter-wave vertical antenna or Marconi antenna. There are also parabolic reflector antenna used for terrestrial, microwave, and satellite communications. This is the dipole antenna. There are also other types of antennas for different applications. So far, we are going to explain the half-wave dipole antenna. A dipole antenna is a linear metallic wire or rod with feed point at the center. Okay? And dipole antenna has two symmetrical radiating arms, quarter wavelength, this is quarter wavelength. So far, half wavelength. And this is the feeder. And in this animation, red one shows the voltage and blue one shows the current. Okay? And then I'm coming, the half-wave dipole antenna, also known as doublet or Hertz antenna, as mentioned. The length is approximately equal to the half of the wavelength in free space, both ends of an equal potential with respect to center point. And the radiation resistance is 73 ohm. And we can calculate the wavelength from this equation. So lambda is equal to C over F. This is, and here C is the speed of light and F is the frequency in hertz. So far, if we want to make clear if the antenna radiates at 600 megahertz, what would be the half-wave dipole antenna length? So in this case, we can calculate using this formula. The half lambda is 0.5 meter, and then half-wave dipole antenna length is 0.25 meter. The answer from here, and then you can calculate using this formula for different frequencies. And if you have difficulties, you can contact, then we can discuss further. Then we are coming to the current and voltage waveform. At the center point, we can see the current is maximum and voltage is minimum. It makes convenient point to feed the antenna. The dipole antenna has an electrical half-wavelength long because it becomes resonant. In this case, the inductive and capacitive components cancel each other, so the load becomes purely resistive, and it makes feeding the half-wave dipole antenna far easier. And then the impedance in free space is 73 ohm, which presents a good match of to 75 ohm coaxial cable feeder, and this one is the reason. And for coaxial cable was chosen for many applications. And here the field strength of half-wave dipole antenna, the plot field strength for an antenna at a distance from the radiating element to see the radiation pattern. The vertical field vector for field can be calculated using the following this equation. I is the current distribution, R is the distance from the origin, E theta is the far field vector, and using this formula it is possible to calculate the radiation pattern of half-wave dipole antenna from far field vector. So far, the radiation pattern and directivity. So using this formula, it is possible to calculate radiation pattern and hence determine the directivity as mentioned. So far, the maximum half-wave dipole directivity shows the maximum radiation at right angles. That means 90 degrees to the main radiator. Angle theta is here. Angle theta in the half-wave dipole formula can be used to determine the far field strength. So far, we understand the half-wave dipole antenna. We want to compare that on half-wave and full-wave dipole antenna. So half-wave is circular type, full-wave dipole is elliptical radiation pattern. Here half-wave length is lambda over 2, here length is lambda, and then for half-wave dipole, most of the radiated signal transmitted closer to the horizon, so less losses, but a full-wave dipole antenna radiates signal wasted to the sky and loss is high. So far commonly used half-wave dipole antenna and comparatively less used for full-wave dipole antenna. So for the design tips of half-wave dipole antenna, we have to consider hints and tips that would be useful for optimum performance of the antenna. Use balanced feeder or balun because it is a balanced antenna and require balanced feeder. If coaxial feeder is needed, then to be used from balun must be used. Half-wave dipole antenna is not a half-wave and is not the same as half wavelength in free space. So far, voltage maxima at the antenna ends. In this case, the points of the maximum voltage at the ends of the antenna, and it is, if used for transmitting, make sure that this cannot be accidentally touched because voltage is high, and also need to ensure that adequately insulated. So the conclusion of my presentation, half-wave dipole antenna is most commonly used, and its radiation pattern is circular type and wavelength is lambda over 2. Radiation resistance is 73 ohm, which is closely to the 75 ohm as coaxial cables, and cascade impedance of some transmission lines are close to the radiation resistance of half-wave dipole antenna. For my presentation, I use the selective references as listed here. And if you have any question, feel free to ask me or send email as provided in my first slide. And thank you very much for your attention.